So in our previous example, we had two gases that interact. If gases don't interact and don't react, we just assume ideal interactions where they can just hit off of each other like pool balls on a table. And that means we can assume that each gas molecule exerts the equal amount or pressure associated with that gas. What that means is if you have, let's say, hydrogen and oxygen, okay, by themselves without any outside source, they're not going to interact. But there's a pressure associated with oxygen and a pressure associated with hydrogen. If we put those into a balloon, the total pressure is the sum of the pressure of the oxygen and the pressure of the hydrogen. We call this Dalton's law of partial pressures. So if you have a mixture of gases that don't react, we can sum up the partial pressures to find the total pressure. So let's take our reaction that we just did and say, okay, we formed NO2. After NO2 is created, there's no more NO in there. So the only things inside the stopcock, or inside the gas containers, are NO2 and O2. And that's everywhere. Okay? So we have some NO2 and we have some O2. Okay? Each of those are exerting its own pressure, so they're not going to react and form anything else. So if we calculate the partial pressure of NO2 being 0.401 and the partial pressure of oxygen, doing some other kind of math and calculating the excess, we got 0.2969. When we add them together, the total pressure of the volume, or the given volume, is 0.698. Because when we do adding, we go by the least amount of decimals. Like I said, we can fill up a gas with, or a balloon with two gases that don't react. And we can say that, we can pretend that the balloon, okay, with the mixture, we can pretend that the oxygen is by itself and the hydrogen is by itself, and calculate its properties, its moles, and things like that. The Dalton's law of partial pressure implies that each gas within the mixture does not interact, okay, and behaves as if it was alone. What's lovely about this ideal scenario is we can relate the amount of the pressure, the ratio of the pressure, to the moles. And this is because if you look at and rearrange the ideal gas law for pressure, we get nRT over V. Assuming that the volume and temperature are the same, and R is, of course, is a constant, all of these cancel out. So what you're left with is the pressure of a gas over the total pressure inside of a container. And that is proportional and is equal to the ratio between the moles of the gas and the total moles. We give this fraction a name. So both of these represent a part over total. But what this does is allows us to calculate what we call the mole fraction. So you might see it as an x here, or like a chi if we're a little bit more correct. And chi is a unitless fraction that tells us how much gas takes up in a total mixture. So we can put these two equations together. The P1 over P tote is equal to N1 over N tote, which is equal to chi of your gas. we can rearrange and we can say that the partial pressure of a gas is equal to the mole fraction, or basically how much is in there, over the total pressure, or multiplied by the total pressure. So if a gaseous mixture contains 0.53 atmospheres of hydrogen, nitrogen, and oxygen at different amounts, what is the mole fraction of hydrogen? So this case, we're not looking at the total, we're not looking for the moles, we have atmospheres, but we know that the mole fraction, N1 over N tote, is equal to the pressure of our gas over the total pressure. So we can relate the mole fraction to the pressures. So we don't have to convert to moles or anything like that. We can just take this ratio. So we know that we are looking for H2, and this is a problem on your worksheet. So H2 has a pressure of 0.53 atmospheres. And then our total pressure is the sum of the pressures of everything in there. So we have hydrogen, but we also have, we also have nitrogen. And we have oxygen. And if you can't read my writing, I will be posting up the answers to this online. So if we do this, we can get our answer. And I'm not going to give this to you. No, I'm not going to give this to you. I would like you to work it out on your own, following through, and go ahead and calculate the partial pressure for nitrogen and, don't know why that's not working, and oxygen. Okay, there's something wrong with my pen. And what we'll notice, though, is that the pressure total has to equal, not the pressure total. The mole fraction, because it's a fraction, right, has to equal 1. Because it's a fraction, so you have parts over total. So if you sum up all the partial or all the mole fractions, it should equal to 1 because you have 3 things. Each of those have a certain amount. But overall, your fraction should be 100% when you add them all up. So I want you to go ahead and solve for the partial pressure of H2, N2, and O2. And I'll post up videos if you want me to with the answers to that. The answers to this will be online. Okay. Pay attention to sig figs. Oh, here it is. Yeah. This is for oxygen. I'm going to skip over nitrogen. So the kinetic molecular theory takes these gases, these ideal gases that are bouncing around in a container, and explains the movement a little bit. So we know at this point, we know a relationship between pressure and volume, temperature and volume, volume and moles. We also know how to combine all those into the ideal gas. We know how to use the ideal gas in order to calculate moles, and we can go back to chapter 3 and 4 material as necessary with the moles, because now that opens up all these conversions and dimensional analysis and things like that. What the ideal gas law and all these gases, all these relationships are telling us is more on the macroscopic scale. So we see the pressure increasing or decreasing and things like that. And again, watch those videos that I posted, like the little fun videos. That gives you like examples. But what these gas laws gas law failed to do is describe the atomic level. What is actually happening to these molecules that cause pressure to increase or decrease? So we talked a little bit about this on Wednesday, where pressure is a measure of a force, and it's basically collisions off to the side. And so we talked about a party. If you go to a party, if you have a small volume and 50 people inside your dorm, you know you're going to hit a lot, okay? You're going to run into a lot of collision. There's going to be a great force, pressure exerted in the room. If you go take the same 50 people into the convocation center, it is more spacious, and so there's less collision, and so the pressure is less. And so what we're talking about by collision is describing the velocity, mass, and the collision, how that describes pressure. And we can assume that when we have a mixture of ideal gases that don't interact and don't react, that everyone's bouncing around like pool balls. Okay? And that's why we can use the Dalton's law of partial pressures, because we're not assuming anything sticks, they just hit and go. Okay. What this microscopic level is telling us is there are random motions. So gases consist of a large number of molecules, and they're always in motion. And it also tells us about, it still makes the same assumptions as the ideal gas, where there's not a lot of volume, and that the attractive and repulsive forces between the gas molecules are really non-existent, not affecting anything. Okay. A couple things I do want to point out, and I think these are some questions on your handout, is that there's a relationship between kinetic energy and temperature. And we learned this from 1101. That as kinetic energy increases, the temperature should increase, and that's because you have more movement of molecules. So the energy of these molecules, these kinetic energies, this movement, is proportional to the absolute temperature. And this energy, remember, one of the laws is energy cannot be created nor destroyed. It has to be transferred if we're going to or it could be transferred though. So energy can be transferred between molecules during collision. So you think about playing pool, and I always go back to this because the idea is transferring this kinetic energy. You hit the cue ball to hit the other ball to make that move. Same thing happens to molecules. Okay? The average kinetic energy of a molecule does not change with time as long as the temperature of the gas remains constant. So there is a direct relationship between kinetic energy and temperature. So as long as temperature remains the same, the average kinetic energy does not change. Okay. We can trace where these molecules would go, how these molecules would travel. And we describe that as effusion or diffusion. So effusion is an escape from a small hole where the gases go through. Diffusion is the spread of a substance throughout a space. So it doesn't have any barriers, and it can go wherever it wants. But in both of these cases, you'll see that the gases flow from high concentration to low. Okay, and I think that is one of the questions on your handout. It might take a direct route. It might take a roundabout way, but we'll go from high concentration to low concentration. And really what I want you to take away from, you don't have to learn the names or anything like that, but what I want to describe is that the lighter the gas, the faster it goes. Okay? So when we talk about kinetic energy, it's easier to move around if you are smaller, and that kind of makes sense, right? Sumo wrestlers are good at what they do, but they're not going to win a marathon. You see those marathon runners are usually very skinny and made to run long distances. And they